Hi everyone, and welcome to our discussions about astronomy. In this first unit, we're going to just take a brief overview of the universe and the night sky and all of those other things that get people interested in astronomy. So in this very first discussion, we're going to just get a sense of our place in the universe. So some typical credits. And the textbooks that I tend to go by are mainly just what are in here, as well as a whole bunch of my other sources. What I mean by in here is just in these notes. But there is a very good free online textbook that can be found at OpenStax. It's constantly being updated, and some of their explanations are some of the best that I've found for this level of astronomy. So, without further ado, basically, I like to sometimes put Calvin and Hobbes in some of these just to put things in perspective. So here, if you want to pause and read the panel, but Calvin is thinking that there should be a charge on the universe so that we keep out all of the riffraff. But here is our place in the night sky, so to speak. We can kind of imagine a person looking up at the night sky, but what we like to use as a sort of visual aid is this idea of a celestial sphere, this really, really big dome that's centered on a person, and onto which you have the projections of all of the stars and the planets and everything else that can be in the sky. So first, just a broad outline of the rest of this PowerPoint, and what we will mainly hit in this particular video will be an idea of the scale of the universe, because the universe is really, really big, and to get a sense of how incredibly awesome it is, it helps to just kind of compare things in the universe with everyday objects. So that's what we're going to get into after we introduce some units. So first we have kind of a little depiction of our solar system. This is not to scale, ironically, but it does show the planets roughly to scale with each other in terms of size, not in terms of their orbits around the sun. I mean, first of all, the sun is not right up next to Mercury, Venus, and Earth like this, taking up over 90 degrees in the sky. That would be really bad. But in terms of the relative sizes of, for example, Jupiter compared with the Sun, that's about right. Jupiter and Saturn compared with Uranus and Neptune, that's pretty close to being about right. And Earth compared with these planets as well. The sizes of the planets and other objects are about right, but their distances are not. So units of measurement. In this course, we will often use the SI system of units, the international system, the so-called MKS system, where meter is the unit of length, kilogram is the unit of mass, and second is the unit for time. Notice that it's the kilogram that is our mass unit, not the gram. That just helps to make sure that many of our various equations aren't off by weird factors of 1,000 or anything like that. So a lot of times, though, just speaking in terms of everyday numbers, we often introduce Greek prefixes. For example, 100 centimeters are in a meter. And to remember that there are 100 centimeters in a meter, consider the fact that there are 100 cents in a dollar. So 100 centimeters in a meter, 100 cents in a dollar. A lot of people confuse centi and milli, but just 100 cents in a dollar, 100 centimeters in a meter. So a millimeter is 1/1000th of a meter. So literally the prefix itself tells you what it is. It's a multiplier. And this is a nice table of all of the Greek prefix multipliers. In fact, one of them is even a Greek letter. Micro is 10 to the minus 6th. What that means is that whenever you see this prefix in front of a number, that means in front of a unit, that means multiply that unit by that number. So, for example, a gigaparsec would mean like, okay, here we go, giga is 10 to the 9, so 10 to the 9, that is 1 billion parsecs. What's a parsec? Well, we're going to get to that later. Some common non-SI units in astronomy are things like the astronomical unit. The astronomical unit is the average distance between Earth and Sun. And it's convenient when describing objects that are on the size scale of our solar system. For example, Neptune orbits at about 30 astronomical units from the Sun. In other words, the size of Neptune's orbit is about 30 times the size, at least in terms of each dimension, as Earth's orbit. A parsec, which we just mentioned before, is actually a special unit. It's a weird unit. It's something that kind of comes from geometry, but it's defined to be the distance away from our solar system that an object would have to be, such that as Earth goes around the sun, that object's position in the night sky relative to background stars and background galaxies would change by 1/3600th of a degree over the course of a year as Earth orbits around the sun. It's a very small angle, 1/3600th of a degree, and it means that an object would have to be pretty far away in order to traverse that amount or less. In fact, it turns out it's about 3.26 light years. Now, the parsec is something that comes about from this idea of trigonometric parallax, which we're going to get into later on a little bit, but I'll just mention it now. It's kind of like, okay, you can imagine putting a finger at right in front of your nose, just a few inches in front of your nose, and looking at it with your left eye and your right eye closed, and then looking at it with your right eye and your left eye closed. Well, you'll notice that your finger seems to move with respect to the background objects. That's because you're looking at it from a different perspective. Well, as Earth orbits around our sun, the closest objects, like planets and then the nearest stars, are going to appear to move a little bit with respect to background stars and background galaxies. And if it moves by 1 degree, that would be mean that the object's relatively close to us. If it moves by 1/60th of a degree, that is 1 arc minute, then that means it's 60 times farther away than an object that would move by 1 degree. And if it moves by 1/60th of an arc minute, that is 1/3600th of a degree, or 1 arc second, then that would mean that it is 1 parsec away. It's just the parsec is defined to be that distance. So, in fact, that's where the term comes from. It exhibits trigonometric parallax over 1 arc second, parallax second parsec. So, it works. Now, what you will often hear more in everyday language, like when you read news articles or popular magazine articles about astronomy topics, are units of light years. For example, certain stars are so many light years away, like Betelgeuse is something like 600 light years away from Earth. So a light year, it's a unit of distance. It is not a unit of time, although you can think of it as a unit of minimum time for a given distance. In other words, if something is 600 light years away, then that means that anything that you see happening there actually happened 600 years ago. So in that sense, it's kind of like a unit of time, but we generally think of it as a unit of distance. So a parsec is also a unit of distance, in spite of the impression that you might get from some of the Star Wars movies. But yeah, a parsec is about 3¼ light years. So, some examples of using those prefixes along with some of these units. So, this picture is a really nice picture. It's composed of a lot of ionized hydrogen gas. Well, the wavelength of light that will ionize a hydrogen atom is 91.2 nanometers. So if you go back to that table, nano being 10 to the minus 9, so 91.2 times 10 to the minus 9 meters. Well, that's pretty short wavelength of light. That's ultraviolet light. Our eyes see in the wavelength of about 400 to 700 nanometers. We'll talk about that in a future unit. But anyway, that nano prefix helps us here. In other words, we don't have to write it as 0.00000000912 meters. The prefix comes to our rescue, as does scientific notation there. Scientific notation means, like, okay, if we were to write this in scientific notation, that would be 91.2 times 10 to the minus 9 meters, or 9.12 times 10 to the minus 8 meters. Another use, 1.42 gigahertz is the wavelength of hydrogen that you often get in giant molecular clouds when you have a hydrogen atom going from spin up to spin down. That emits a photon with a wavelength of about 21.1 centimeters and a frequency of 1.42 gigahertz. Or how about Kilo? The radius of Earth is about 6,400 kilometers, or 6,378 kilometers along the equator. So there's our scientific notation. We already mentioned that before. And it not only does it help us to make really big and really small numbers tractable, at least easy to write, not necessarily easier to think about, but at least easier to write, but it also automatically tells us the number of significant figures, significant digits that is, that a number has. So for those of you who had all kinds of nightmares in chemistry class about trying to figure out how many significant digits a number has, well, if you write it in scientific notation, you always know. In other words, however many digits you write in front of the multiplier, in this case 7.42, 5.10, each of those has 3 digits. Each of these numbers, therefore, has 3 significant digits. So, and then here you have one with 2 significant digits, and then one with 5, and then one with 5 again. So, again, it also makes it easier to write really big and really small numbers. So now, to understand stuff like this better in the course, we need to get our sense of scale. Now, I do want to warn you that you're going to encounter a lot of numbers in what we're about to say. You don't need to know those numbers. So this is really just to give you a sense of how absolutely enormous our universe is. So consider a typical adult human. So Chief Wiggum here, for example, typical adult human might have a height of about 1.7 meters if we round this to 2 significant digits, and a mass of about 80 kilograms. I assume that Chief Wiggum's mass is a bit larger than that, but in any case, that's a typical adult human. And then from Game of Thrones, Tyrion Lannister, the dwarf, 1.3 meters. Earth, however, so just our planet, our home, Earth, has a radius of 6,380 kilometers. That's 4 million times the height of a human. So it's like you stack 4 million humans one after another. Well, if you were to count up to 1 million, just one number per second, that would take you over 11 days just to count over 1 million. So you would need to stack 4 million humans to go from the center of Earth up to the edge. The mass of Earth, on the other hand, here we're talking about a very large volume, so radius is a one-dimensional thing, but volume is a three-dimensional thing, so mass is going to be associated with, well, volume times density. But the mass of Earth is about 6 times 10 to the 24 kilograms. That is 6 trillion kilograms. That's 7 times 10 to the 22 times the mass of a human. So what would that be in terms of names of numbers? Well, let's see. Trillion is 10 to the 12. Quadrillion is 10 to the 15. Quintillion is 10 to the 18. Sextillion is 10 to the 21. So the mass of Earth is about 70 sextillion times the mass of a typical human. That's really, really massive. So, I mean, this here, 4 million, you can kind of imagine at least being able to count that. So if it takes over 11 days to count that, count up to 1 million, counting once per second and never sleeping, then it would take you about 1.5 months to count up to 4 million. But, I mean, just counting up to 1 billion, which is 10 to the 9th, would take you over 31 years. And counting up to 1 trillion, which is 10 to the 12th, would take you, well, 31 times 1,000, so 31,000 years. Well, 10 to the 22, here we're just talking about unimaginable numbers. Well, there's where scientific notation comes in. It at least allows us to write down unimaginable numbers. So that's just the mass of Earth. So our distance from the center of the solar system is 93 million miles, or about 150 billion meters, or 150 million kilometers. That's about 100 billion times the height of a human. So, and that's just Earth from the sun. Let's scale things out a bit. So there's Earth. Now consider Jupiter, our largest planet. So Jupiter has a mass, so we just talked about how Earth's mass is like 70 sextillion times that of a human. Well, Jupiter is over 300 times as massive as Earth. And its radius is about 11 times Earth's radius. And just a bit of trivia, it turns out Jupiter actually rotates really fast. Its, quote, day is less than 10 hours. So we'll talk about that in more detail when we talk about the solar system later in the unit. Later in the year. And also another bit of trivia is that Jupiter has a moon, Europa, that actually contains more liquid water under its icy surface than all of Earth's oceans combined. We're in the planning stages of sending a spacecraft to go into orbit around Europa and possibly to drop a lander onto the surface that would potentially take samples and give us an idea of whether there's actually life in those oceans. But yeah, liquid water under the surface of Europa. So just kind of one of those cool things that's really far out there. So more pictures of Jupiter. And even this storm right here, the Great Red Spot, in this particular picture, from one end to the other, this was over about 2 Earth diameters. Now this is an old picture of the Great Red Spot. It's actually shrank a bit since then. Shrank. But now it's more like 1.5 Earth diameters from side to side, but it's still pretty big. Now, our sun. Our sun is about 2 times 10 to the 30th kilograms in mass. So it's something like 1,000 times the mass of Jupiter. So 300,000 times Earth's mass. So remember again, Earth was like 7 times 10 to the 22 times the mass of a human. Well, our sun is 300,000 times that massive, or as massive as that. And its volume is enough to contain 1 million Earths. It's also 100 times the radius of Earth, or 100 times Earth's diameter. So our sun, really, really big. Luckily, it's really far away. It also contains almost 99.9% of the mass of our solar system. Again, we're encountering a lot of numbers here. You don't need to know these things. But I'm going to mention that 99.9% bit often throughout the course. And by the time we get through our solar system unit, you'll get used to that. It's what we call a main sequence star. What that means is something we'll talk about in our 7th unit when we talk about sun and stars. And you can kind of think of the size of our solar system as being on the order of about 100,000 astronomical units in diameter. That is 100,000 Earth-Sun distances. So a radius of thereabouts like 50,000 astronomical units. What I mean by that is that's kind of the extent of our sun's kind of gravitational influence, if you will. Outside of that, the force of gravity of everything else in our galaxy starts to overwhelm the force of gravity from our sun, so things wouldn't really bind well to our sun's gravity outside of that distance. So that's why we think of that as a representative size scale of the solar system. Neptune is much, much, much closer than that. Yeah, our solar system's a really big place even after you get past Neptune and past things like the Kuiper Belt where you have all kinds of Pluto-like objects. It's actually the Oort cloud of comets that might extend as far out as perhaps 50,000 astronomical units. So, solar system, it's a really big place. And just give a sense of scale, this feature on our sun, this is probably bigger than Earth. So again, the astronomical unit is a good way of describing solar system scales. And like Earth's orbit, it has a radius of 1 astronomical unit. Mercury is about 0.4 of those, Venus is about 0.7, Mars is about 1.5. But Neptune is 30 of them out. It's 30 astronomical units away. Pluto on average is about 40. But yeah, as I mentioned, out much farther than that, you eventually get to the Kuiper Belt, which isn't really a disk. It's actually more like a spherical cloud. So beyond that, you don't really consider our sun's gravity to be important because our galaxy's gravity becomes more important after that. What about within our galaxy, getting outside of our solar system? The closest star to our sun is an object called Proxima Centauri. It's something called a red dwarf star. It's, ironically, even though it's the closest star to our sun, it's so dim that you need binoculars or a telescope to see it. So you cannot see it with your unaided eye, even though it's the closest star to our sun. So it's 4.24 light years away from our sun. Now, how big is a light year? Well, remember how big an astronomical unit is, 93 million miles? So a light year is over 63,000 astronomical units. And the closest star to our sun is over 4 of those. So that's, again, just giving you a sense of how really big things are out there. Now, what about distance to Betelgeuse? So about 700 light years earlier. I guessed 600, so my number was a little off. Betelgeuse is this kind of bright orangish red star in the shoulder of this constellation that you might know. This is the constellation called Orion. And there's the kind of shoulder, one shoulder is Betelgeuse. This other shoulder, Harry Potter fans, is a star called Bellatrix. Ooh. And then the star down here is called Rigel. That's about 860 light years away. These are actually two of the brightest stars in the sky. Why are they so bright? Because intrinsically, they actually are really bright stars. They are much brighter than our sun. If you were to replace, like, for one thing, if you were to put Betelgeuse in place of our sun in the solar system, its outer layers would actually go past the orbit of Mars. And Rigel would actually be a bit smaller than that, but it's also much hotter, which, as we'll discuss in a future unit, means that overall, that means it's going to be a lot brighter. So, something that I already mentioned is that it's like, oh, the closest star to our sun, Proxima Centauri, is one you can't even see. Well, what about the stars that you do see? Well, guess what? The stars that you see in the night sky are not a very good representation of what is actually out there in our galaxy. The vast majority of stars are much, much, much smaller and dimmer than the ones you typically see in the night sky. The ones that are bright enough to be seen in the night sky, a whole lot of those stars are actually exceptional. Now, there are a few exceptions. For example, there's a star called Sirius. Yeah, a lot of Harry Potter characters are named after astronomical objects, but Sirius is the brightest star in the night sky. Why is Sirius so bright? Well, because it actually is one of the closest stars out there, and it's somewhat bright on its own. But a whole lot of the stars you see are actually really, really bright on their own. In fact, the brightest stars that you see in the constellation Orion, Betelgeuse, Bellatrix, Rigel, Saiph, these three stars in the belt, Mintaka, Alnitak, the stars that make up the Orion's head called Maesa, as well as the stars that are lighting up the Orion Nebula over here like a firecracker, as well as this star right here called Sigma Orionis, as well as this star right here. All of those stars are actually so massive that they're going to end their lives in supernova explosions. Come back in 20 million years, all the stars in Orion are going to be gone. They will have exploded. Too bad, so sad. These are exceptional stars. A whole lot of the stars that you see in the night sky are exceptional stars. They do not make up a good representation of what's actually out there in our galaxy. But it does make for a really nice night sky, especially if you live in a dark area, which if you go to the school that I'm teaching this for, you don't. Too bad, so sad. But if you visit a dark area, you'll get a better idea of what the night sky really looks like. Now, the Milky Way galaxy. Our galaxy contains about 400 billion stars, including those very smallest, dimmest ones, which actually make up most of the stars in our galaxy. Things like Proxima Centauri, the closest star to our sun, is one of those so-called red dwarf stars. On a clear, dark night, you can typically see about 5,000 stars in the night sky at any one particular time, from a very dark, clear area. Now, as I mentioned, you're seeing, to a large extent, exceptional stars. So, our solar system is about 27,000 light years away from the center of the galaxy. That's really, really far. So light takes 27,000 years to reach us from the center of the galaxy. It's often really fun to think about astronomy in terms of what were things like on Earth or in our solar system at the time that light from certain objects was emitted. So, in some cases, from the most distant objects, Earth wasn't around. The diameter of our galaxy is about 120,000 light years. So modern humans did not yet exist when the light from the other side of our galaxy began its journey toward us. So this is an artist's depiction of our galaxy. So there's the center of the galaxy over here. There's where our sun would be. And in fact, now they have kind of upgraded this and called it simply the Orion Arm. But so yeah, we live in a legitimate arm of a spiral galaxy. And from one side to the other is about 120,000 light years. So that's really, really far. Here's kind of a look-alike galaxy. This is a real picture. You can't get a real picture of the Milky Way because, I mean, our galaxy is so big. How would you get it? You'd have to send a spacecraft above it. That would take a very long time. And we've been putting things in orbit since the 1950s and sending things away from Earth orbit since the 1960s. So definitely not long enough. But this galaxy is a very nice example of what we think is a Milky Way look-alike. So if you were actually to take a real picture of our galaxy, this is what it would look like. This artist's depiction mainly serves to kind of highlight various features, but this is a real galaxy. There's kind of another Milky Way look-alike if you didn't like the last one, or if you think Milky Way is kind of more like this. And there's a zoom in to the bar in the center. Yeah, we live in a barred galaxy, a barred spiral galaxy. So think about the distances we've discussed so far. I mean, first the solar system on the scale of astronomical units, where one astronomical unit is the average Earth-Sun distance, about 93 million miles. And then light years, where a light year is something like 63,000 astronomical units. And then a typical star that you see in the night sky is on the order of tens of light years away from us, sometimes hundreds of light years. Some of the really intrinsically brightest ones are thousands of light years away. For example, the star Deneb, which is the brightest star in the constellation Cygnus, that's about 2,600 light years away. So why is it so bright? Well, because it's actually in truth about 700,000 times as bright as our sun. So that's why it looks bright to us, even though it's thousands of light years away. But when you talk about distances to other galaxies, you need to start speaking in terms of millions of light years. The nearest large galaxy to the Milky Way is the Andromeda Galaxy. That is about 2.5 million light years away. So when light from the Andromeda Galaxy, which looks like a faint fuzzball in our light-polluted skies, if you can see it at all in the constellation Andromeda, it looks like a very, very faint fuzzball on the best nights. If you go to a place with better night skies, like central rural parts of, say, Virginia or a lot of other states, then the Andromeda Galaxy looks like a more obvious cloud in the constellation Andromeda. But it's 2.4 million light years away. So when that light that makes up that cloud that you see with your very faintly with your unaided eyes began its journey to us, the pre-human species Homo erectus did not yet even exist at that time. The Andromeda Galaxy itself is actually a pretty big galaxy. Its diameter is over 200,000 light years, so that's over 1.5 times the diameter of the Milky Way galaxy. And we actually think it contains over 1 trillion stars. And as we'll discuss later in the course, the Milky Way and the Andromeda Galaxy are on a collision course. That's going to be a spectacular light show in about 4 billion years. And then the Andromeda Galaxy and the Milky Way, as well as another one called the Triangular Galaxy, they make up a small cluster of galaxies called the Local Group. But that small cluster is just one of many small clusters in something called the Virgo supercluster, which is a gravitationally bound structure, and everything that's, at least these galaxies are gravitationally associated with each other. And it's actually galaxy superclusters that are the largest gravitationally associated entities in the universe. The center of the Virgo supercluster, which is just something called the Virgo cluster, contains a bunch of galaxies in it, including some really gargantuan galaxies. So one of those is called M87. It's actually this object right here. This thing has several trillion stars in it, and at the very center of it, it has a black hole. And the mass of the black hole that's at the center of this galaxy right here, M87, has a mass of about 6.4 billion times the mass of our sun. So we'll talk about black holes more later in the course. But even the Virgo supercluster, we used to think that the Virgo supercluster was the largest thing, gravitationally associated thing of which we are a part, but we now realize that the Virgo supercluster itself is part of an even bigger supercluster called the Laniakea supercluster. So you don't need to know the names of these things yet, by the way. we're just kind of introducing how really big things are. The Laniakea supercluster is about 500 million light years wide, and it contains about 100,000 large galaxies. So 500 million light years. So just the time that it takes light to go from one side to the other. It's like, okay, what was going on Earth 500 million years ago? Well, fish had evolved and other sea creatures had evolved, but life on land did not yet exist. So that was it. I mean, okay, fine. You had bacteria and fungi and stuff like that, but okay, multicellular life on land did not exist 500 million years ago. So this was a very different time. So this is kind of a depiction of the Laniakea supercluster, combining also with some velocities of some of these things that help us to understand how gravitationally associated with each other things are. The Milky Way in this depiction is around here, I believe, in this picture, but it's just truly an enormous structure. So we live on Earth, which orbits the Sun. Our Sun orbits around the center of the Milky Way galaxy. So just as the planets orbit the Sun, our Sun is one of many stars that orbit the galaxy, and the galaxy itself is part of a cluster of galaxies, which itself is part of a supercluster of galaxies. So that's really just how things are. Now the universe as a whole is expanding. So what that means really is that space itself is expanding, and galaxy clusters, and a lot of times individual galaxies within those clusters, go along for the ride during this expansion of space. Now, the rate at which the universe is expanding is something called the Hubble constant. We're going to discuss that in a lot more detail when we get into the cosmology unit and how that relates to how fast things are moving away from us with distance. But the point is that when you live in an expanding universe, that means that the farther away things are, the faster they are moving away from us. And those of you who have a bit of background understanding things related to modern physics might wonder, like, well, does that mean that there is a certain place in the universe where things are expanding away from us so fast that you can't see them because they would be going faster than the speed of light? And the answer is yes. And the extent of that is what we call the visible universe. And the universe is about 14 billion years old. That was when the Big Bang happened, about 14 billion years ago. So what that means is that the extent of the visible universe is about 14 billion light years away from us. But there's a whole lot more out there even past the extent of the visible universe that we can never measure, but we know that it's out there. So, looking across the universe, this is an amazing picture. A lot of these galaxies in here are part of this cluster that's about 2.2 billion light years away. It's the cluster called Abell 1689. And it also is a nice example of a gravitational lens. There's so much mass associated with this cluster that these galaxies that you see right here, these are actually much farther away than the galaxies in the cluster itself, but you kind of see this looks like kind of a tunnel here. This is an example of gravitational lensing. There's so much mass here that it bends the path of the light around the cluster and magnifies it as well, and also distorts it, so you get these distorted galaxy images. A lot of these are actually the same galaxy, just viewed from different angles, which is also kind of neat. We'll discuss that in more detail when we talk about cosmology as well, and also when we talk about general relativity. Okay. Now, the edge of the universe. This is a picture called the Hubble Ultra Deep Field, and some of the galaxies in this picture are around 10 billion light years away. So we're talking about truly ancient structures. 10 billion light years away. Well, wait a second. The universe is only 14 billion years old. Well, that explains why a lot of these galaxies look kind of funny. Galaxies hadn't really quite finished forming a couple of billion years after the Big Bang. So when you look at galaxies that are a couple billion years after the Big Bangs, in other words, 12 billion light years away, you're looking at the universe as it was before it had finished forming. Astronomy is the only scientific field in which it is possible to directly observe events of the distant past. In all other scientific fields, what you are observing are relics of the past. For example, in paleontology, when you look at dinosaur bones, you're looking at relics of creatures that existed tens of millions or hundreds of millions of years ago. But you're not able to actually look at the creatures themselves. But in astronomy, you are actually able to observe the universe as it existed, say, 6 billion years ago, when you look at a whole bunch of objects that are 6 billion light years away. Or 8 billion years ago, when you look at a whole bunch of objects that are 8 billion light years away. In other words, we can actually directly observe the evolution of the universe. And the study of that is called cosmology, and we have an entire unit dedicated to that. But yeah, I mean, it's incredible to realize that you can actually directly observe the distant past in astronomy because of the fact that the speed of light is finite. Now, the very most distant view that you can have is something so far away, the cosmic microwave background radiation, that it requires a special type of telescope called a microwave telescope to be able to see it. But this is essentially the leftover afterglow of the Big Bang. The Big Bang, as you can imagine, was a very energetic event. The universe was very hot during that time. But wait a second, we talked about the fact that the universe is expanding. It's been expanding ever since the Big Bang. And what does an expanding gas do? It cools. So what was originally a red-hot gas, well, due to the expansion of the universe, has cooled such that instead of being red-hot, it then shifted into infrared hot. Now it is only microwave hot. In other words, you need a microwave telescope to be able to see that radiation. Well, we have built microwave telescopes, and this is the image that we've gotten from it, the Planck Observatory as it is, after those microwave signals have been gathered up and then depicted in the using visible colors just to make them visible to us. But the different shapes and sizes here depict what would eventually become galaxy clusters based on just small gravitational anomalies that existed after the Big Bang. So these features are about 14 billion light years away, 13.8 billion light years away, we think, to be a little more precise, though I will mention that there's a little bit of a fight over what this exact number is. There's one group of scientists swearing that it's about 13.8 billion light years, another group of scientists swearing that it's about 13.6 billion light years, and the uncertainties that each group has are smaller than the difference between the numbers. What does that mean? It could mean new physics that we are on the verge of discovering. So stay tuned. We might end up getting some more news of that, perhaps even as early as the end of the school year. So I'm going to kind of skip through the rest of this. I'll mention that based on that picture that we have in that last slide and analyzing it in great detail, we not only understand the age of the universe, but also its energy content. The universe is about 68% dark energy. In other words, a completely different type of energy than anything we understand. And even among the matter that's in the universe, about 85% of the matter that's in the universe is actually in the form of dark matter, which is also something that we do not know about. In other words, we know that it's there because of its gravitational influence, but we don't know what it is. We do know what it's not. We know that it is not anything that has ever been produced in any laboratory scientifically. It's nothing that we have ever discovered. We are still trying to figure out what composes the dark matter. We also know that it doesn't interact with light, and it might interact with the weak nuclear force. Again, this is something that we will talk about in a lot more detail later in the course. So right now I'm just trying to kind of give you a mind-blowing feeling of the universe that's out there. In other words, the vast majority of what's out there, we have no idea what it is. So as I've mentioned already, when we see objects that are so many light years away, we are simply seeing them when the light was emitted, which means that when you observe different parts of the universe that are different distances, you're actually observing the universe at different times in its history, making astronomy really, really special. So yeah, a lot of these galaxies were, the light from those was emitted when the universe was, say, like only about 1 billion years old. Others, the brighter ones, are more recent. In other words, quote, only about 2 billion light years away. So they look like more normal types of galaxies. But the really weird ones were when the universe was a very different place, which is why they were so weird, because the universe, they hadn't finished forming yet. So here's another really nice example of a gravitational lens and a whole bunch of galaxies. So that's very important. I want to stress again how important it is, the fact that when you look at something that's so many light years away, you're seeing the universe when it was that many years younger than it is today. And one of the big predictions of Big Bang theories is that when you look at the universe very far away, it should look very different than it does today. Whereas alternative theories generally say, oh, it should be pretty much the same at all times. But we now realize that that's not true. So early galaxies are kind of weird looking things like this, whereas galaxies today are more mature looking, so to speak. So there were a lot more quasars early in the universe. We'll talk about quasars in more detail later in the course, but long story short, they have something to do with black holes, and they are really the active cores of galaxies. So as I mentioned, the observable universe goes to the edge of what you can actually see. In other words, things that are beyond the observable universe are more than 14 billion light years away. In other words, that light has not yet had enough time to reach us yet. And in fact, it turns out it never will, because those things are expanding away from us faster than the speed of light as well. So that's an unfortunate thing, in a manner of speaking. We will never be able to observe the unobservable universe. It's not just unobservable now, it is forever unobservable. Sorry. So, another little Calvin and Hobbes cartoon. So, Calvin talking about the cloud of stars is our galaxy, so I guess he lives in a reasonably dark area where you can actually see the Milky Way itself, and our solar system's at the edge of it. This cartoon was printed in the 1980s when they actually thought that our solar system was at the edge of the galaxy. Okay, well, 1990 according to the copyright. Anyway, we now realize that that's not true. And Calvin's saying, we hurl through an incomprehensible darkness. In cosmic terms, we are subatomic particles in a grain of sand on an infinite beach. So kind of thinking about that mind-blowing idea. It's like, oh, wonder what's on TV now. And I was like, what? Okay, so here is something to think about before we sign off from this video. So a lot of people think that our tiny physical size in the vast universe makes us insignificant, whereas other people think that our ability to learn about the wonders of the universe gives us significance despite our small size. This small size being something that we have been stressing throughout this video so far. What do you think? Do you think that we are insignificant because we pale in comparison with the universe, or that we are significant because of the fact that we can comprehend the universe? And with that, we'll sign off, and I thank you all for watching this video. Have a good one.